This is lecture 1 of 2 for the online lectures to make up for February 21st when I was missing class, where we're discussing Chapter 8, Metabolism. So rather than having a 1 hour long lecture, I decided to split these up into 2 shorter lectures so that you could look at it, step away if you need to, and then be able to go back to it. So if you went to Wiocast already, you'll see that all of this is together there in one lecture, but there's no audio, which is why you're probably watching this on YouTube right now with me giving you a voiceover rather than the standard Wiocast lecture. So as we left class on Wednesday, we were talking about the fact that electrons are what we use within cells to drive our energy, and that we store those in bonds. And so again, if we remember the first rule of thermodynamics, it's that energy is not created or destroyed, it's just transferred or changed. And so again, if we have an electron out here like we see, and that it ends up getting pulled closer to the atom, it ends up having lower potential energy as it moves closer to the nucleus, because you're going to have to put more in to pull that same atom away. But in the reactions that we drive, if we pull that closer to the nucleus, in the lower potential energy that we have, it might give us some actual kinetic energy in some shape or form that we have, that we can see designated here as possibly heat or light. This might also draw mechanical energy to do some sort of work within a cell. And so we're going to start there and talk about the ways that we might go about moving these electrons within a cell to create any of these effects. And so with that, we're going to discuss chemical reactions. And so chemical reactions, broadly speaking, occur when substances or molecules are transformed into other substances or molecules. And so this happens through the breaking of bonds and the formation of new bonds to create these new molecules or substances. And again, matter is never created or destroyed, so everything that you have on the start you have to have in some way, shape, or form on the back end of this. And so typically we'll see chemical reactions designated as a linear progression from reactants to products. So reactants are what you start with, products are what you end up with after the reaction. So what we have is in our reactants that the bonds there are going to be broken, and then we're going to have new bonds formed, and those end up being our products. And so again with this, because matter isn't created or destroyed, nothing is created or lost, we just have rearranged all of the elements or all of the atoms that are involved. And with the possibility of the electrons moving there, we may end up with having our products that have higher potential energy or lower potential energy as compared to the reactants, which we can then use energetically in some way, shape, or form. As we look at this, we're going to diagram reactants to products in a chemical reaction. And so typically you'll see this written as some sort of equation where we have our reactants on the left side, we have our products on the right side, and it's going to show the kind of reaction that's able to progress, and also everything that's involved that we have. So you'll note that the reaction that we're writing out here is if we have carbon dioxide as a gas and we add that to water as a liquid, we can get carbonic acid, which is a new covalently bound form of both of these that we have. And so you'll note that when we do these reactions, that we'll note the states that they have. So we can see that the G stands for gas, the L for water stands for liquid, and then the AQ for carbonic acid means that we have an aqueous solution where this is dissolved in water. So we're not going to have all of the water turning into carbonic acid. It's going to be dissolved in water. So you might also see that we have an S for solid, which is going to be written in here in just a second on the side. And it's important to have these state designations because, as we're going to talk about later, some of what's going to drive a reaction or not might have to do with whether it gains or loses order. And so as we look at this, we want to know if we're going to gain or lose order in the system. So the other thing that we want to do here is make sure that we have the same amount of molecules or atoms on the front end of the reaction in our reactants as we do in the products in our back end. And so we can balance that like a standard equation. And so if we're going to look, we want to see that on the left side you can note that we have one carbon. And then on the right side, in our products, on the right side of the arrow, we have just one carbon. So we don't have to do anything with carbon. And then we can look and we can see that there are 2 hydrogens on both sides. And then adding the 2 oxygens from the CO2, the 1 from the H2O, we have 3. So this reaction here is already balanced. We have the same number of atoms on the left side and the same number of atoms on the right, so we don't have to work with anything. So an example of another reaction that we might use is hydrogen gas with oxygen gas making water. And you'll note that for oxygen gas, it's O2. And so here in just a minute, I'm going to add a 2 to the oxygen. And you can see also that on the reaction above that we made the arrow double-headed, which means that it's able to run in either direction there. So, but in our hydrogen gas plus oxygen gas making water reaction, if we go to look at this and balance it, we're going to see that it's not balanced. So we can start out again and we can say that there are 2 hydrogens on the left side, 2 hydrogens on the right side. And so our hydrogens initially are going to be balanced, but if we look at our oxygens here, we'll see that there are 2 on the left and only 1 on the right. And so we're not able to lose an oxygen here, and that means that we're going to have 2 water molecules. So now we have 2 oxygens on the right, 2 on the left, but that creates an issue with our hydrogens in that we have 4 on the right and only 2 on the left. So we know that we're going to need 2 molecules of hydrogen gas and 1 molecule of oxygen gas, that with a lot of energy put into it to make this happen, we're going to end up making 2 molecules of water. And so what we can see is that we have a balanced chemical reaction, so we know what's going in on both sides of this in terms of what we're going to use. So the next question that you might have here as we do this is, why was it so important that I correct the arrow up top, and why do we have a difference in the arrows in these 2 reactions that we're looking at, and is that meaningful? So the answer, of course, is yes, that it's meaningful. It's not something that we would do if it wasn't meaningful, and I wouldn't have made sure to correct it if there wasn't meaning to it as well. So in defining this, that first reaction is able to run either to the left or to the right at equilibrium. And so where we have that double-headed arrow, it's going to run either direction spontaneously to equilibrium. And so, like you can see us noting down here, we're going to note that the first reaction is able to run or occur spontaneously in both directions. The second reaction, however, is not able to run spontaneously in both directions. We know that water doesn't just split into hydrogen and oxygen gas very easily. Additionally, we know that hydrogen gas and oxygen gas don't just form water very easily. Both directions on that second reaction require significant energy input. And so for that second reaction, because of that significant energy input, we have the single-headed arrow, and there's no way that it can get back without having significant energy input and a little bit of infrastructure to go back. And so we might see water split into hydrogen gas and oxygen, but we're probably going to have to hit it with lightning or something along that line to be able to get it to run back the other direction with a significant amount of energy put into it. So some key terminology that we want to make sure to define from these ideas is, what does it mean to be a spontaneous reaction? And we're going to talk about that a fair bit here in energetics, especially early on. So a spontaneous reaction is a reaction that's capable of proceeding without requiring outside energy. So meaning that the reaction itself is energetically favorable enough that it doesn't require a big push, say, from the outside to make it happen. This does not necessarily mean that this reaction is going to occur instantaneously, or that there's not still an activation energy hump, which we'll define later, that we need to get over, but it means that it's energetically favorable enough that we don't require outside energy to run this reaction. So spontaneous reactions and the ability to be spontaneous is going to be largely defined by 2 terms that we're going to discuss here. So the first of those terms, or the first concept that is going to play into whether or not a reaction is going to be spontaneous, is the idea of entropy. So entropy is in nature a measure of disorder. So if entropy is increasing, it means that disorder is increasing, or that the order has decreased. So that brings us to, we've already discussed the first law of thermodynamics, which is that energy is not created or destroyed. So the second law of thermodynamics has to do with entropy. And the second law of thermodynamics states that entropy in an isolated system will always look to increase. So in a natural system where it's isolated, we're going to move towards more disorder. And this has to do with diffusion, or it has to do with movement or anything like that that we're looking at. In nature, you're always going to see entropy increase in a closed system if it has the ability to do so. And so that's our second law of thermodynamics. And so it's favorable in a biological system for more disorder to come in. The second concept that is going to define if reactions are spontaneous or not, or that's going to come into play, is enthalpy. So enthalpy, and there's some definitions here that you're going to see that I write in and scratch out, and verbiage that the book uses that I'm not a big fan of, but I'm writing them down so that way if you see it on a homework or anything along that line that you have it. But enthalpy largely has to do with heat required or given off in a reaction. So when we're talking about enthalpy, we're discussing the heat requirement. So does a reaction need heat or energy, possibly in some other form, but typically heat, to be driven, or through the reaction running itself, is it going to give off heat or possibly potentially other energy? Which is why, again, your book discusses it as potential energy increasing. I prefer to think of that as heat because it's less easy to confuse with Gibbs free energy, which we're going to see later. So rather than just talking about potential energy with the heat regarded, we're going to talk about potential energy of the whole reaction. So there are the two terms that we're going to see in regard to enthalpy and whether or not it requires or gives off heat. So the first one is endothermic, and then the other one is exothermic. And so much like we saw in regard to endocytosis and exocytosis in class on Wednesday, we have the same headings. Endo means into, exo means out of. And so thermic is just talking about heat. So endothermic means that heat is required to go into the reaction. So the reaction is not going to run without some sort of input of heat. In that, again, the verbiage from your book is that the potential energy increases, so you put some heat in there, it adds energy to the system, and you're able to create more potential energy. But again, I feel like the easier way to remember this is that it just requires heat input, endothermic, heat in. And so we need to have some energy going in to drive the reaction. So an exothermic is the flip side of that coin, where through the reaction we are going to give off energy or give off heat. And so what we'll see in that, again, as noted by the book, is that the potential energy typically decreases, but your entire potential energy also brings your entropy into account, which is why, again, for the enthalpy I like to look at it through the eyes of heat. So does it require heat for the reaction to run, or do you give off heat in running the reaction? And so these two factors come together in combination to determine if the reaction is going to run spontaneously or not. And they're going to define for a whole reaction if our free energy or our overall potential energy is going to increase or decrease. And so we define this by Gibbs free energy, which is our G number that you'll usually see, or our delta G number. So Gibbs free energy is a calculation that we utilize that accounts for both changes in entropy, so our disorder, and in enthalpy, which is our heat requirement. So are we adding or subtracting heat? Are we adding or subtracting disorder? And those two things coming together are going to determine if our overall reaction is energetically favorable or not energetically favorable. So as we write this out, you'll see that entropy, or change in entropy, is designated by delta S, and change in enthalpy is designated by a delta H. So that delta is a Greek letter that you'll quite often see that just designates change. So when you see delta, it means change. And you guys might have seen this in lab already, where you were diagramming some reaction rates that you would have the change in concentration over the change in time. And so you might be familiar with this from your lab already, but again, you see delta, it means change. So our Gibbs free energy is typically designated as delta G. So change in the overall energy in the system from the reactants to the products is what our delta G is. So in driving the reaction, is it energetically favorable or not? And we define that as delta G. And so the delta G is calculated utilizing the equation delta G equals delta H minus T delta S. So we have the change in enthalpy, so do we add or subtract heat? The change in entropy, do we add or subtract disorder? And then we also take the temperature into account. As you guys have seen in lab, many of the reactions that you're going to run are going to be affected by temperature changes, and so it does definitely matter the temperature that you're running at. So utilizing this delta G equation, we're going to fall into one of two categories. So the first one that we're typically going to see is an exergonic reaction. So an exergonic reaction is one in which we have a lower free energy in the products than we did in the reactants. So the overall potential energy in the products is lower than that we started with. And so this means that we have an energetically favorable reaction. So it's more easy to go to this because when you have lower potential energy, you're more likely to be stable. So in these cases, our delta G is less than 0, or we might also say that we have a negative delta G. So overall, we have less energy on the product side than we do in the reactant side. And we can say that this is energetically favorable. So it's going to release energy overall in this reaction, and it's going to be spontaneous typically. So if we look at some of the reactions that we've seen in class, our exergonic reactions are going to be similar to our hydrolysis reaction, where in the end we add some chaos because we're breaking polymers into monomers. It's going to be energetically favorable in doing that because we're creating disorder, so we have a negative delta G, we give off energy, and so it's going to be more likely to drive without requiring energetic input into it. So we need water, we get energy out of it, so it's going to have a negative delta G. So there are a couple ways that we can have that negative delta G. So the first one is if we have an exothermic reaction. So if you give off a lot of heat, it means that that energy has to come from somewhere. You go from high potential energy to low potential energy. You give off heat rather than requiring heat to drive it, and you're more likely to have a negative delta G. The other way that we're going to end up with a negative delta G or an energetically favorable reaction is if we increase entropy. So again, based on that second law of thermodynamics, nature is always going to move towards disorder. And so if we have a reaction that is going to drive more towards disorder, it's going to be more energetically favorable, and we're more likely to be spontaneous. So that's the first situation of what we might have in terms of free energy. Our second situation is an endergonic reaction. So endergonic reactions are reactions that are not energetically favorable. They're going to require energy to drive them. So in that, our products are going to have higher free energy than our reactants. So we have a higher potential energy in our products than we do in our starting material. We're going to see these with a delta G that is greater than 0, or we might also say for these cases that our delta G is positive. So when you have a positive delta G, you're not going to have a spontaneous reaction because it's not energetically favorable. And then we can say that these require energy input, and because of that, they're not going to be spontaneous. So you're not going to be able to happen anytime you want to with a reaction if you are requiring energy from the outside. You're only going to have that reaction work and be favorable when that energy is there, and so it's not going to be able to happen in a spontaneous way without something on the outside pushing it. So again, looking at this, in terms of what can give us a negative delta or a positive delta G. So the first thing that's going to drive this is an endothermic reaction. So if you require heat in this reaction to make it work, you're going to be reliant on that heat to run. And naturally you're going to need energy to push this reaction. The other thing that's going to give us a positive delta G is if we increase order, or the other way to say that is that we decrease entropy. And so this is why when we do the polymerization reactions with the condensation reactions, we're taking monomers and we're putting them together in a much more ordered way. And so by adding that order, it's energetically not favorable, and so we have to put energy in to do that. So we add energy, it puts monomers, or it puts monomers together into polymers, and we're able to make it happen, but it does require energy to drive this reaction. So we can go ahead and graph these reactions in such a way that we're able to see them visually. So if we put together a graph here, and on our, what am I drawing first? On our y-axis we've got free energy, or the overall potential energy of the system, and then on the x-axis we have the reaction progress. So if on the left hand side here we add our reactants, and then on the right hand side we add our products, and we'll go ahead and label those here. So what you can see here in this graph is that our reactants have an overall higher free energy than our products. And so where they have an overall higher free energy, the potential energy overall, or the free energy, is decreased from the reactants to the products. So we have a negative delta G. So looking at this graph here that we have of our free energy over the reaction progress, is this reaction going to occur spontaneously or not? So hopefully you looked at this and said, because it has a negative delta G, it's energetically favorable and it's going to occur spontaneously. And so we're going to run from our reactions on our left hand side to our products on our right hand side, and we're not going to be fully reliant on outside information, or outside energy to make this happen. So again, we see a negative delta G, and so we're more likely to have a spontaneous reaction. So moving to the other side here, we're going to draw a similar graph that again has free energy on our y-axis and the reaction progress on our x-axis, and we're going to add reactants and products just the same. However, we can see now that our products on the right hand side have a delta G that's positive, so there's more free energy, or more overall potential energy, in your products than in our reactants. So looking at this where we have a positive delta G, again, answer to yourself, is this going to be spontaneous or not? So this is not going to be a spontaneous reaction because we have a positive delta G. So either we're adding a lot of order or requiring a lot of heat for this reaction to go, and therefore it's going to be reliant on those outside factors to run. So in terms of looking at these chemical reactions, even if a reaction is spontaneous, so if we have a negative delta G and it's able to run without outside energy, chemical reactions still aren't just going to happen all of the time, or like I said, instantaneously when things come into contact with one another. So there are a couple things that need to happen for a chemical reaction to be able to take place. So the first thing that we need to have happen is we need to have our two reactants collide in a precise orientation. So as we've talked about, when we're breaking bonds and then putting bonds together, to make a covalent bond, we're going to have electrons in valence orbitals that aren't full come into contact with other electrons in valence orbitals that aren't full. So if we had an example down here of us trying to create water from the oxygen, and we'll just have elemental oxygen here rather than oxygen gas, and elemental hydrogen, so say the lightning split, we're in that millisecond where everything has been turned elemental and these are going to come and react together. we need to have this hydrogen come and bind the oxygen over here where we have a valence electron free and a valence electron free. So we need to have it hit where its orbital is, where the open orbital on oxygen is. If it's going to come in and so let's redraw this. So if it's going to come in and try to hit oxygen up here where its orbital is already full, it's not going to bind, and you're going to have the negative charge of those electrons repel the negative charge of the electron and the hydrogen, and you're not going to form a bond. So for this to happen, you still have to have your atoms collide in the precise orientation that they need to have happen to make a bond. So the second thing that we need to have happen for a chemical reaction to take place is that this collision between our reactants needs to have enough kinetic energy to overcome the repulsion forces between the electrons that are interacting to be able to make a bond. And so like I noted in the previous example, if that hydrogen, the bottom part, hits those oxygen electrons up top that are filling their shell, it's going to repel. But even if the hydrogens hit the oxygen at the right orientation, you're still going to have a negatively charged electron and a negatively charged electron that are coming into contact with one another that in general would like to not have to interact there. We've got the negative charge and the negative charge that we're going to have some repulsion. And so what we're going to need to have happen is enough energy bringing that hydrogen electron into where that oxygen electron is so that we can have them start to spin around one another and actually create a bond. So this hydrogen is going to come in here, it's going to collide with the oxygen. We can see that it's in the proper orientation, which we need first off for it to happen, but then we need to have enough energy that the one oxygen's electron doesn't push away the one hydrogen electron, and we can start to have them rotate around. We get dipole forces, and then boom, we have a bond. And so let's go ahead and draw a hydrogen on the other side that's going to do the same thing for us. So it's going to come in, it's got its one electron, it's going to collide in the precise orientation, and with enough energy that those electrons are going to fill that one shell, we're going to share, we're going to have a bond. So this kinetic energy that we need to have to overcome this repulsion we refer to as our activation energy. So again, our activation energy is the amount of energy needed to happen to start a reaction. So it's the amount of kinetic energy that even if you collide at the precise orientation that you need to have for those electrons to form a bond. So if we go back and look at our diagrams from before of our Gibbs free energy, we've got our reactants on the left and we've got our products on the right. And so the way that you'll typically see these drawn is that now we also have our activation energy added to it. And so the activation energy, or the plateau of the activation energy, is where you see I'm sorry, not the plateau, the high point of the activation energy is where you see the most unstable part of the reaction. We call that the transition phase. And so the distance in free energy between your reactants and the top of that is what we consider to be the activation energy. So again, from your reactants to the high point on this curve is the amount of kinetic energy required to get over that hump and actually make a reaction start. And so again, this distance here is our activation energy here, and this distance on the left that you can't see is the activation energy there. So again, even if a reaction's spontaneous, you need to have enough energy to get it over this hump to get a reaction started. So if we look at this as it has the figure in your book, we can see that we have reactants on the left-hand side, products on the right-hand side, and then the activation energy, which is the hump that we have to get over. So, looking at this reaction, is this reaction going to be spontaneous or not? As we can see here, we have a negative delta G, so we have less potential energy or free energy in our products and our reactants, energetically favorable, so it's going to be spontaneous. Nonetheless, we still have to get past this transition state, which is the most unstable portion of this reaction. So we have to have our activation energy come in, we get to pass the transition state, and overall we'll end up with more products than reactants, but we still have to be able to cross that bridge to be able to have this reaction go. So this concludes the end of the first part of our metabolism lecture. That's the makeup for February 21st. So the second part of this lecture will have to deal with what we do to get across this hump, and then the specific role that enzymes play in our biological systems.